Welcome to our discussion on the transformations of functions. We're going to start off by defining what a transformation is. And a transformation of a function is basically shifts and stretches. If you can move a function left or right, up and down, stretch it, squash it, flip it over a line, basically any kind of manipulation you can think of, we'll call that a transformation. Simply put, if you have a generic function like the absolute value of x, when you add a 2 to the outside of the function, can you see how this is acting on the outside of the function because the function itself is doing the absolute valuing, if that was a verb. That's going to move your function up, right? That's going to transform the graph of this function by shifting it vertically. And then the -3 on the outside will shift it vertically down 3 units. So you get vertical shifts up and down by adding numbers to the outside of a function. You just have to be able to recognize what the base function is. So if we're talking about f of x equals the square root of x, then that's your base function. And if you put a +2 on the outside, right, that's the outside of the function. But if I put a +3 in there, that's inside the function because the square root is acting on it, right? So this would be on the outside, but this one would be on the inside. So the 2 would shift it up and down. The 3, as we'll see here shortly, shifts it left and right. So things inside the function shift it left and right. Things on the outside of the function shift it up and down. Here's the graph of the original function, absolute value of x, and then x plus 2, shifted up. There's the other one, shifted down. Now we can use our knowledge of vertical and horizontal shifts to graph a whole new set of functions. If we know what a regular function looks like, we now know that if we add a c to the outside, it moves up, and if we subtract a c from the outside, it shifts down. So basically, if you add a number to the outside, it goes up. You subtract a number, it goes down. Okay, what about inside? Well, I've already kind of let that cat out of the bag, right? We now know that these are going to be horizontal shifts. But these are a little tricky because your instinct would tell you that this x minus 2 on the inside, right? We started with just x being squared. And now can you see how everything inside the parentheses is being squared? So we've added that -2. Your instincts might tell you that that is going to move 2 units to the left, right, in a negative direction. But unfortunately, the ones on the inside go opposite. So this one will actually shift to the right, and then this one will shift to the left. And the way to remember that for me as a student was, think of the easiest value, and I usually go with 0, right? What happens to the function at 0? When I plug a 0 in, I get a 0 out. Well, so if I know anything about the x squared function, I know that its vertex right here is at 0, 0, right? That's where it touches the x-axis. And then when I have x minus 2, I always ask myself, okay, what value do I now have to plug in for x in order to get back to the case of evaluating 0, right? Because I know when I plug in 0, I get 0 as an answer. What do I now have to let x equal so that I will have 0 being squared? And that's where you go, oh, I've got to plug in 2, right? Now when x equals 2, 2 minus 2 is 0, and I'm back to that same answer of 0. So this point now shifts over here to x equals 2. And it reminds me that it's a shift to the right. And then the same kind of logic works here. If I want to get back to having 0 squared, I have to put a -3 in here. So it's shifted from 0 over to -3. So that's how I always remembered it. Here's the graph, seeing those shifts left and right. This is talking about the kind of the same idea. If we're looking for an x-intercept, that's what I was talking about with put in x equals 0 and then figure out what y is. Well, if we're looking for the x-intercept, that's where y equals 0, so you set it equal to 0 and solve. So it's kind of the same thing, but it's a little trickier to try and have to solve for something. So I like my idea of just trying to get that 0 back as the thing that's being acted on. So let's look at another example. How about something as simple as our original function being f of x equals the square root of x, and then we want to look at how about f of x equals the square root of x plus 3. Again, if we put 0 into the function to get 0 out, what do we now have to put into that function so that we're still taking the square root of 0? And you hopefully see we have to put in negative 3, so this one gets shifted to the left by 3. Kind of what they're talking about here, but I think my way is a little cleaner. This can get a little confusing. Okay, so to sum it up, horizontal shifts, right, are kind of counterintuitive. When you have x minus c, that means you shift that many units to the right, whereas x plus c shifts to the left. Now we can look at functions that have multiple shifts and be able to figure out what's going on. If we know what the original simple function looks like, if we know what that looks like, we should be able to graph this one fairly simply, because what's happening? The negative 3 on the outside is shifting it down by 3 units, right? And the plus 2 on the inside is shifting it to the left by 2 units. So start with the generic picture and move it down, move it over, and there's your new graph. This is just talking about how you can do that, in a general sense with C's. And again, don't get bogged down in formulas. Don't worry about the whole C thing. You just know that if it's a number, right? And they're just trying to generalize it by saying if c is bigger than 0, so for a normal, positive number, we know what f of x minus c is going to do, we know what f of x plus c is going to do, etc., etc., etc. So they're just generalizing what we already understand, and then here they're just doing the same thing with a d for the outside. And here's a nice pretty graph, right? We start with our generic square root of x. The minus 3 piece shifts it down by 3, and then over by 2 for the plus 2. What they did is they first shifted it to the left and gave you the blue one. Then they shifted it down and gave you the final answer, which was the red one. But you can see how it would be the same both ways, right? If we shifted down first, we would have something that starts here at negative 3 and looks something like that. And then we shift it over by 2 units and we're back to the red line. So it doesn't matter in which direction or which one goes first. Normally we do it by order of operations. So I would have done the inside first, right? So that's why they shifted it to the left first, because you do things inside the parentheses and then you come out and do things outside the parentheses. But you will get the same both ways. How about reflections? So we can reflect things over the x-axis or the y-axis. If we have a negative in front of our function, then that just means every time we plug a number in, we get the opposite number out that we would have gotten originally. Think of something really simple like y equals 2x. Plug in a number, get 2 times it, right? Plug in 3, get 6. Plug in negative 2, get negative 4, etc., etc., etc. Now look at what happens when you have negative 2x. You're always getting the opposites. Instead of plugging in 2 and getting 4, you plug in 2, you get negative 4. Instead of plugging in 3 and getting 6, you get negative 6, etc., etc., etc. So when you put a negative in front of the function, you're just getting all of those opposite answers for y. So instead of getting a positive number, you get a negative. Instead of a negative, you get a positive. And what happens is everything flips over the x-axis, right? This is your x-axis. So we call that a reflection. Here's a good picture. And these little dashed lines just mean that that distance and that distance are the same. So you get this perfect mirror image over the x-axis. Well, what about if you put the negative on the inside of the function? Then you get a flip vertically over the y-axis. Here are some examples. So we start off with our normal function y equals the absolute value of x. When we put the negative 2 on the inside, it shifts 2 units to the right. Right, so we're doing inside first. Then the next step, we now use the negative on the outside, right? Order of operations, we move and see, okay, what's being multiplied by it. And that makes it flip top to bottom. So now it's kind of been turned upside down. And then finally, the last one is to put the plus 3 on it, which shifts it up. And there's our final solution for what the function looks like. So if you know a little bit about the family of functions, right, you know a little bit about what general functions look like, you know what absolute value looks like, x squared, x cubed, square root, all those types of things, then you can figure out what the other more complicated looking functions look like just by doing flips and shifts and stretches and other types of transformations. Here's another example. This one's going to look at stretching and compressing, or what I like to call stretches. Instead of stretching and compressing, it's all the same more or less. We're going to now multiply a function by a number rather than just the minus sign. Right? The vertical flips that we had before happened when we just put a negative sign in front of the function. We were basically multiplying by -1. But now what happens when we actually multiply by a number, 2 or 1/2? And what's going to happen is anytime we multiply by a number bigger than 1, the function is going to grow faster, right? Because all of those answers are now being multiplied by a number bigger than 1 before we get our final answer on the left side. So that's going to be a vertical stretch. It's going to get taller. It's going to grow faster. But if we multiply by something between 0 and 1, a fraction, then the answer we get out of the original function now gets smaller before we get our final answer. And that's going to compress the function. It's going to shorten it. It's going to look squatter, right? Shorter and wider is what's going to happen with that thing. Best thing is just look at some pictures. The blue one, that's our general absolute value. The red one is when you multiply by 2, and the green one's when you multiply by 1/2. So you can see how the red one is being stretched, is being pulled up. It's now thinner and taller, and the green one's being squashed, right? It's shorter and wider. And that's what happens. This is just talking about why it works. But in general, right, and to generalize this, anytime we multiply a function by c, where c is greater than 1, then our function is going to stretch vertically. And then anytime we multiply our function by c, where c is greater than 0 but less than 1, right? It's a positive sorry, that's a 1, not a 1/2. 1. So it's a fraction. Then our function squashes. Maybe arrows pointing at each other, and it kind of widens. Okay? Last but not least, we can use stretching and compression to graph graphs, new graphs, just like we used horizontal shifts and reflections. And we'll ultimately be able to put all of this together all at once. This is formalizing what I had on the previous slide of when you get a vertical stretch versus a compression, and it's all about the size of that letter. They're just using A instead of C. They're reminding us what it means to have a horizontal, didn't realize that typo, a horizontal stretch or compression, right? If you have numbers on the inside, whether it's a b or a 1 over b, now we have horizontal stretches and compressions. So we only talk about vertical stretches and compressions, but just like vertical, the horizontal acts the same way. When you have, the only problem is it's just like before when we put things on the inside of the function and it was counterintuitive. Remember when we had f of x plus 3, that it went to the left, well, look at these rules. They're kind of reversed. Before, when we had the number on the outside and it was bigger than 1, we got a stretch, and when it was between 0 and 1, we got a compression. Now on the inside, it's the exact opposite. So when we have that fraction, that's when we get a horizontal stretch, which if you think about it is kind of the same thing as a compression, right, if it's stretching horizontally. And then when we put numbers bigger than 1 on the inside, we get a compression, right, horizontal compression, which means you're horizontally bringing it in, which is going to, in essence, make the thing taller, which is the same thing as, so it does kind of work the same. They work in tandem. Here's our original function. Some weird, funky thing looks like a parabola with a line stuck on it. And we want to figure out what's going to happen with numbers on the inside. So that's what's happening when you put the 1/2 on the inside. See how it got wider? Right? It's still at a height of 3 there at the vertex, right? From 1, 3, but now you got to go over to 2 in order to get there. So instead of reaching your local maximum with a value of 1, you got to go to a value of 2. You can also see that the little tail has stretched. See how it goes all the way out to -4 now instead of -2? So there's your horizontal stretch. Then when you put a 2 in there, you get a horizontal compression. Instead of going out to 1 to reach that maximum, you only have to go to a 1/2, and instead of that tail going out to 2, it only goes to 1. So there's the stretch, there's the compression, right? Stretch, normal, stretch, compression. Put a negative number in there, it just flips around the y-axis. And then we can put it all together and we can see what happens to a function when we do all sorts of things to it. So we start with our generic parabola, x squared. The -1 on the inside shifts it to the right by 1. The 2 on the outside vertically stretches it, makes it taller. The minus in front of the 2 makes it reflect. And then finally the 3 right in front moves it up by 3, because that would be the same thing as -2 times all that stuff plus 3 at the end. So that's where you get that vertical shift up for that one. Let's look at one last example. What you're looking at on the right is like a cross-sectional picture of an artery. Right? So if you have an artery with a radius capital R, we know that the velocity, which we'll call V, of the blood flow, so how fast your blood is flowing through your artery, is actually a function of its distance from the center of the artery. So the velocity of the blood through the artery is going to change as its distance from the center changes. And that's where this ugly looking formula comes from. Your r squared is a constant because it's the radius of your artery. C is also a constant that's determined for each particular artery, so different arteries are given different constants. And then we can figure out the speed, the velocity of the rate of the blood based on how far it is from the center of the artery. Well, if you just start with the basic function of y equals r squared, right? We're just looking at a basic function involving this because this is our variable, right? This is a constant. This is our only variable. So this really looks just like v of r, right? We know it's a function in terms of r. Is just kind of r squared being transformed. That's how we can think of it. So if we're given an artery with a radius of 3 and some flow constant, right, of 10 to the 4th, then we can figure out what's going on. First thing we want to do is plug those numbers in. So we plug in our flow constant of 10 to the 4th and our radius of 3 and kind of distribute, right? Do the math. 10 to the 4th times 3 squared, which is just 9, and then 10 to the 4th times our negative r, and that's what we get here. Now if we start with our function just being the generic r squared, well, isn't r squared really the same thing as just y equals x squared, but with a different letter. So that's our normal parabola, centered at the origin, going up. What happens to it? 10 to the fourth, right, being multiplied by 10 to the fourth, that stretches it vertically. So now it becomes a really tall, thin parabola. Okay, and then what about the negative? What does the negative in front of it do? Well, that flips it, and now it goes down. It's really tall and points down. And then finally, what does this number that we're basically adding to it do? And that shifts it up by that many units. So here it is. It's shifted up, right? That's a distance of 9 times 10 to the fourth, which is 90,000. It's facing down, and it's hard to see in this picture, but it has been stretched. It would end up being a very thin, very tall parabola in a upside down way. And so from that we can see how fast the blood flows in various places. Now, something to keep an eye on it is that portions of the graph corresponding to negative values of r don't really make sense, because this is no longer just an equation, it's a function. It's supposed to model real world things, and it's a function in terms of r being distance from the center of this artery. Well, that artery had a radius of 3, so really your distance can only go from 0 to 3. So the only part of x that matters is right there. Any x is less than 0 doesn't make sense. How can you be a negative distance from the center? And then any distance greater than 3 also doesn't make sense, because then you'd be outside the artery. Now, technically, you could let a negative distance be kind of distance from the center in the other direction, so it still kind of makes sense to have this part of the graph, and you can see that it's a mirror of this part of the graph, because if you're 1 unit from the center, then that's how fast it's flowing, and if you're 1 unit from the center in the opposite direction, it's flowing at the same rate. Okay, so when we're modeling things in the real world, we have to pay attention to kind of the logic zone. Where does this thing actually make logical sense? That's it.